Hello, my name is Mihaela Gidersa, and I'm gladly welcoming you to our first online meetup. Before we actually dive in, first I want to tell you that today's session will be recorded. So if you want to watch it later again, you can do it. Second, and we actually strongly encourage you to have questions, please write them in the Q&A area of the stream and will be answered at the end of the session. For the ones that join us every time and know what is about with this community, but also for the ones that are wondering what is it with all the posts and all the groups that we are on and all the events, well, what exactly is Yash Software Craftsmanship Community? Who are these people? Well, this is a community for people that care about software, the software they write. We want to hear war stories. We want to hear successful stories, but also failures. We believe that everyone has something to learn and something to teach. It all began after a workshop on, guess what, software craftsmanship by Sandro Mancuso. And for more than a year now, we craft events with the objective of growing the community and doing a lot of knowledge sharing. Some examples of the events are the Code Retreat we had at CodeCamp, the Coding Kata, meetups, but also our monthly book club. Don't forget about the book club. And speaking of the book club, the coolest coincidence happened this time, because the last book that we discussed, it was written by our speaker today. Vladimir Khorikov is here with us to discuss about some of the principles of effective unit testing. Also, he's extremely interested on your feedback on the book. Thank you, Vladimir, for accepting our invitation, and the stage is yours.
Thanks, everyone. All right, so let me share my screen. Okay, you should be seeing the presentation.
Yep.
Okay. All right, so as you heard, my name is Vladimir Khorikov, and today we'll be talking about effective unit testing. A couple of words about myself. As you also heard, I recently published a book, Unit Testing Principles, Practices, and Patterns. And I also have several courses on Pluralsight. Most of them are about domain-driven design, but I also have one about unit testing. So the agenda of this presentation, it will consist of 3 parts. First, we'll discuss how to measure the effectiveness of a unit test. Then we will talk about how to put this knowledge to practice, how to write effective unit tests, and then we will also talk about when to mock and when to not use mocks. Okay. So the first topic is how to measure unit test effectiveness. Unfortunately, there's no automated way to do that. And when we're talking about automated ways to measure test effectiveness, we usually think about test coverage. But test coverage is not the best metric, and it's not a very good one. And that's because it has the following 2 properties. It's a good negative indicator, but it's a bad positive one. What do I mean by that? Good negative indicator means that if the test coverage metric shows that you have some low coverage numbers, let's say anything less than 40 or 50%, then it means that you don't test enough. And that's a good sign that there's something wrong with your tests. But the opposite is not true. Even if you have a high coverage number, it doesn't automatically mean that your tests are of good quality. And I saw a lot of projects where people had good coverage, maybe even close to 100%, and their tests were still a mess. So it means that this metric is a bad positive indicator. The only way to reliably measure the effectiveness of your unit tests is to evaluate each of them separately. And how to do that? There are 4 components of a good unit test. The first one is protection against bugs. The second one is resilience to refactoring, fast feedback, and maintainability. Let's talk about the last two components first because they are easier to describe, and then we'll return to the first two. So fast feedback. Fast feedback is pretty self-explanatory. It basically means how fast your tests execute. And why it's important is because the faster the test is, the quicker you can spot the problems in your code. And as you probably know, a bug that is found during development is orders of magnitude less costly to fix than the same bug that is found in production. And so the quicker, the sooner you find these bugs, the less costly would be to fix it. The fourth component is maintainability, and maintainability consists of two subcomponents. The first one is how easy it is to understand the test, and the second one is how easy it is to run the test. The first subcomponent is primarily the function of the size and the clarity of the test, which means that if your test is small, it's usually quite easy to understand what it does. And of course, the clarity or simplicity of the test also matters, because if you have a test that is that consists of 3 lines, but you have to scroll it to the right, maybe several screens to the right, it's not a good test. And the second subcomponent, how easy it is to run the test, is a function of the number of out-of-process dependencies that this test works with. Such out-of-process dependencies as, for example, the database or maybe external services. And why it's important is because you have to maintain those out-of-process dependencies and you have to keep them operational for the test. You will have to maybe reboot your database, resolve connectivity issues. And so the fewer such out-of-process dependencies your tests deal with, the better, the easier it is to maintain this test. The easiest tests to maintain are the tests that don't deal with any out-of-process dependencies. All right, so that were the third and the fourth components. The first one is protection against bugs, or as I called it in the book, protection against regressions. And bugs and regressions are basically the same thing. They are synonymous. And that component depends on the amount of code that gets executed. The larger this amount, the more code gets executed during the test, the higher the chance that this test will reveal an issue with this code. And also it is important to not only execute a lot of code, but also take into account the importance and the complexity of the executed code. And that's because critical bugs are, they usually appear in domain model or in some complex functionality. And that's where you want to test the most, because such critical bugs, the protection against them provides you with the best value. And also, it's not only your code that matters, but also the code of the external libraries and systems that your application integrates with. For example, as I said, the database or any other frameworks, database, external systems, and so on. And that's important because your application doesn't work in isolation, and you also want to check how your application works in combination with other subsystems and external services. The second component of a good unit test is the most interesting one, and that is resilience to refactoring, or as I called it in the book, resistance to refactoring, but I like the resilience word more. This component tells you how many false alarms you will get from the test after you do the refactoring of the code that this test covers. A false alarm is the same as a false positive, and also it's the same as a false failure. And why this metric is important? So what are the benefits of your unit tests, of your unit test suite? The benefits there are two benefits. The first one is they provide you with an early warning in case you break something. And thanks to such early warnings, you can fix those issues long before your code is deployed to production. The second, benefit of your tests is that they provide you with a safety net. They give you the confidence that your code, that when you change your code, that will not lead to bugs, to regressions. And without such confidence, this second benefit might look subjective, but without such confidence, you will be much more hesitant to refactor your code. And it's important that you don't hesitate to refactor your code, because otherwise your code tends to decay over time. That's because over time you introduce more features, maybe the requirements change, and in order to keep your code clean and on point with those requirements, you will have to constantly refactor that code. So you will have to constantly push against this tendency of your code to decay. And false positives, which is the effect of low resilience to refactoring, false positives negatively affect both of these benefits. They dilute your ability to quickly spot the problem in code. That's because if you get a lot of false positives, you just stop paying attention to those positives because you assume that they are false, and you may, because of that, you can accidentally allow a real bug, slip into production. And also because you have a lot of those false positives, you also don't perceive your unit tests as a reliable safety net. And because of that, you are much more hesitant to refactor your code. But why do we get false positives in tests? False positives are the result of coupling tests to the code's implementation details. So the number of false positives you get is directly related to the way your tests are implemented, structured. The more you couple them to implementation details, the more they break when you modify those implementation details. So let's take an example. Here you can see a class, a message class that consists of 3 properties: header, body, and the footer. You can also see an iRender interface that takes a message as an input parameter and returns a string. The string is a representation, it's an HTML representation of that message. And we also have the message renderer class that implements this iRender interface, and it has several sub-renderers, and also it has the render method that takes an instance of a message, delegates the work on parts of that message to sub-renderers, and then aggregates all the output of those sub-renderers together and returns back to the caller. And those sub-renderers, the header, render, body, and footer render, they look like this, so nothing complicated. They also inherit from the iRender interface, and they work on parts of the message. They wrap it into tags, and that's basically it. So again, here is the message renderer class. And the question is, how can we test this message renderer? There are 2 ways to do so. The first one is to check the content of this sub-renderers collection. And when we check it, if the content of this collection is correct, then we can assume that the behavior of this class is also correct. And here is how this test will look. So here we instantiate a message renderer, we get the list of its sub-renderers, we make sure that the number is indeed 3, and then we verify the types of those sub-renderers. And this technique is called structural inspection, and it is an anti-pattern. It is an anti-pattern because this test couples to implementation details, and therefore it is fragile. So if we modify those implementation details, this test will fail, and it will do that regardless of whether we actually break anything in this functionality in this method or not. So for example, we can rearrange the sub-renders, but keep the observable behavior intact, or we can even remove all the sub-renders and do all the work inside the message renderer class itself, but this test will still break regardless of whether we do the refactoring correctly. And so this test breaks precisely because it couples to implementation details. It's an example of a fragile test. Here's another example, and what this test does is it reads the content of the message renderer class and then checks that this class is implemented correctly. Again, of course, this is a contrived example. It's basically a ridiculous test. You never want to do that, but it's not that different from the previous example. They both couple to implementation details, and both of these tests will fail whenever you modify those implementation details. Of course, this particular test will fail more often because here we can just put any additional line or space and it will break. But still, they are pretty much the same. And this practice is called source code inspection, and it's as bad as structural inspection. The only way to avoid false positives in your tests and improve their resilience to refactoring is to bind them not to implementation details, but to the end result. If we take again the example with the message renderer, then the end result, the check of the end result would be to verify the HTML that this render method returns. And that would be the end result of this operation. And here's how this test looks. So here we also instantiate the message renderer. We supply it with some message, and then we verify that the output HTML is correct. And that test doesn't couple to implementation details, and that's an example of a good test. It verifies the end result and not implementation details. So here is this diagram that shows you, well, the good test answers the question of, is the end result correct? The bad test answers the question of, is the process correct? And that leads to fragile tests. You don't ever want to verify the process or implementation details, because that process or implementation details tend to change often. So these are the four components again, and let's talk about the relationship between the first two components. They are related to each other in this way. So here you can see the test accuracy metric, and it is also known as signal to noise ratio, where the signal is the number of bugs a test finds, and the noise component is the number of false alarms or false positives that the test raises when it finds all those bugs. And the first component, protection against bugs, it is responsible for the signal metric. And the second component, resilience to refactoring, is responsible for the noise component. And both of these components, signal and noise, they are critically important. That's because even if the test doesn't produce any noise, if it cannot find any bugs, so it doesn't produce signal, its value turns to zero. It's close to zero because, well, you want your tests to find bugs. And the opposite is also true. Even if your test is capable of finding any bugs in your code, if it does this with a lot of noise, then its value also approaches zero, because you are simply cannot differentiate between true positives and false positives. All those findings are lost in all this irrelevant information. So in other words, the protection against regressions, against bugs component, it tells you how good your test is at indicating the presence of bugs. So that's the signal component. The noise component is, it tells you how the test how good the test is at indicating the absence of bugs. And again, both of these components are critically important. A lot of problems with a lot of unit tests, they take place because people don't pay proper attention to the second component. So I see a lot of projects where people do pay attention to protection against bugs, fast feedback, and maintainability, but don't, but not so much to the resilience to refactoring component. And as I said, all these four components are important, this diagram shows you why people often don't pay proper attention to resilience to refactoring. So here you can see the two lines, the false negatives and the false positives. And again, a false negative is when your test tells you that the code doesn't contain a bug, but in fact, in reality, this code does contain a bug. So the test cannot find this bug. And that's what the first component, the protection against bugs component, protects you against. It protects you against false negatives. The false positives are the opposite of that. It's when your test shows you that there is a bug in your code, but in reality, there is no bugs. And that's the responsibility of the second component, resilience to refactoring. So here you can see how they affect the project, the unit test suite, with the duration of that project. False negatives, the missed bugs, they are important pretty much from the very beginning. And that's because you do want your tests to notify you if you do something wrong pretty much, well, from the beginning of the project. But the false positives are not that important, at least in the beginning. And that's because the importance of refactoring itself is also not immediate. Because when you start the project, all the code is clear, it's clean, shiny, and only when you continue to evolve and develop the project, only then you start having this necessity to refactor your code. And with that necessity, it also becomes important to not have many false positives. And because if you have those false positives, you will just lose trust in your test suite and will not be as well. You will not do as many refactorings as needed to maintain the project. And also, an interesting part is how the first three components of these four components are related to each other. They are mutually exclusive. So protection against bugs, resilience to refactoring, and fast feedback are mutually exclusive in a sense that you cannot maximize all three of them. You can only maximize two of them at the expense of the third one. And let's take some examples. Here is an example of end-to-end tests, or sometimes they are called functional tests. And these are the tests that verify your application end-to-end, including the external dependencies, such as the database and any other external services that your application works with. These tests have the best protection against bugs because they verify a lot of code and also integration with external services. They are also resilience to they also have the best resilience to refactoring because they are they are as distant from implementation details as possible. But the drawback of these tests is that they provide you with slow feedback, and because of that, you cannot cover all your code with just end-to-end tests. And if we draw the first three components in this way, with these circles, then we can put end-to-end tests at the intersection between resilience to refactoring and protection against bugs, because they have good resilience to refactoring and protection against bugs, but they don't have fast feedback, don't provide fast feedback. Also, we can come up with the second type of tests, and that is trivial tests. Trivial tests are tests that cover some trivial functionality. So here, for example, you can see on the left the user class that have just a simple name property, and on the right there is a test that covers that code. It assigns a name and then verifies that this name contains the correct string. So the benefits of such tests is that they are fast, they have good resilience to refactoring, but they don't provide you with the good protection against bugs. And that's because there's just not much room for a bug in this code on the left. It's just too simple. And we can put trivial tests to this intersection. They have good resilience to refactoring, they provide fast feedback, but they don't protect you against bugs. And similarly, we can come up with a third bucket, and that third bucket is fragile tests. You also saw an example of a fragile test earlier, and here's another one. On the left, you can see a user repository that gets a user by ID and records the last executed SQL to some public property. On the right, you can see a test that verifies this user repository. It tries to get a user with ID 5 and then checks that the last executed SQL contains the correct SQL. So the good thing about this test is that it also executes fast. It has a good protection against bugs, and that's because, well, you can make a mistake in that SQL, and this test will point that mistake out. So it does provide you with a good protection against bugs, but it does that with a lot of noise. It doesn't have a good resilience to refactoring, and you can see here the four alternatives to the SQL, and if you modify your SQL statement to any of these alternatives, you will get the same result, but still the test will still fail because it binds to the implementation detail. The SQL is that detail. It doesn't have anything to do with the end result. If we go back to our circles, we can put fragile tests at this intersection. They provide fast feedback, they have good protection against bugs, but they don't have good resilience to refactoring. And this intersection between all these three components, this ideal, unfortunately, it is unreachable. So you cannot have tests that have the maximum in all three components, but you can still approach this ideal very well. So you can make your tests as close to this ideal as possible, and that's what we'll be discussing next. So we discussed how to measure the effectiveness of a unit test, and now let's talk about how to put this knowledge into practice and how to write effective unit tests. In order to write good unit tests, you have to refactor your code, the underlying code base, and that's because your tests are inherently connected, inherently coupled to the code that they cover. There's no way to decouple them. And if you, how to refactor the code? There are two dimensions that you can use to categorize all the code in your project. The first dimension is complexity or business importance, and the second dimension is the number of collaborators. The first component, the complexity and importance, the resulting test, the tests that cover this code, they have the best value because they provide you with the best protection against bugs. And that's again because critical bugs tend to appear in exactly this part of your code that is either complex or important for the business, basically business logic. On the other hand, if your code has a lot of collaborators, and a collaborator is a dependency that is mutable. So for example, if you test a user class and this class has a dependency on another domain class, let's say company, then this company, if it's mutable, then this company is a collaborator for that class. as opposed to, for example, number 5. If you supply number 5, then it is not mutable, it is immutable, and so it is not a collaborator. So the larger the number of collaborators of the code, the higher the maintenance costs of the tests that cover this code. And that's because in order to test the system under test, you will have to bring all those collaborators to the required state, and then maybe even verify their state and collaborations, the collaborations between the system under test and those collaborators, those dependencies. So that affects the maintenance cost of your tests. And also, it's not only the number of collaborators that matters, but also the type of those collaborators. Because if you have out-of-process dependencies, out-of-process collaborators, then it becomes even harder to maintain the test, because, as I said earlier, you will have to keep those out-of-process dependencies operational. And if we plot these two dimensions into diagram, then we will get these four quadrants. On the y-axis, we have the complexity and domain significance dimension, and on the x-axis, we have the number of collaborators. So on the top left quadrant, we have the domain model and algorithms, and that's the code that is complex or important and at the same time doesn't have a lot of collaborators. Ideally, it shouldn't have any. On the bottom left, we have the trivial code. Examples of this code are, well, in C# it would be one-line properties or trivial constructors that don't do anything other than assign some private fields with some values. On the bottom right, we have controllers, and this is the code that doesn't do any complex work on its own, but instead it delegates that work to some other components. So it does the orchestration, usually between the domain model and external dependencies such as the database. And on the in the top right quadrant, we have the overcomplicated code. That's the code that has both has high complexity and also have a lot of collaborators. An example here are would be something like fat controllers. That is controllers that don't delegate complex work anywhere and do everything themselves. In terms of the unit testing, the unit testing of the left top quadrant, the domain model and algorithms, gives you the best return on your effort. That's because the resulting tests are highly valuable and cheap. They are valuable because the underlying code is complex, and therefore testing that code provides you with the best protection against bugs. And they are cheap because they don't have a lot of collaborators. Trivial code shouldn't be tested at all because the resulting tests will have close to zero value. It's just basically not worth it to test this code. As for controllers, you should test them, but only briefly as a part of a much smaller set of the overarching integration tests. And we will talk about that integration test later. The most problematic type of code is the overcomplicated quadrant. It's problematic because it's hard to unit test because all of those collaborators, but at the same time, it's too risky to live without unit test coverage. And one of the main reasons people struggle with unit testing is because of this overcomplicated quadrant. So how to deal with that? In order to make to improve your code and therefore tests, you have to split this overcomplicated code. You'd have to refactor it into domain model and algorithms and to controllers. So basically, you need to adhere to this principle saying that the more complicated or important your code is, the fewer collaborators it should have. And how to do that? There is the pattern that is called the humble object pattern that will help you do exactly that. So here you can see the task that targets the overcomplicated code, and this code is overcomplicated because it contains a hard-to-test dependency. And, the humble object tells you that basically you should split the logic part and the hard-to-test dependency into separate pieces, and then create a wrapper on top of them, which would be the humble object that wouldn't do anything on its own, but it will coordinate the work between these two components. And after you do this split, you will be able to test only the logic part without involving the hard-to-test dependency. And there is a good metaphor that will help you to think about this split. So here you can see the rectangle on the left. It is wide, but it is short. And the width here represents the number of collaborators this code has, and the tallness represents the complexity of that code. And you can see that the controllers are wide, but they are short. And that's because they work with a lot of collaborators, but they themselves are not that complex. The domain model or algorithms are the opposite of that. They are complex, and that's why I displayed them as tall rectangles. But at the same time, they don't have a lot of dependencies. That's why they are narrow. And your code should be either tall or wide, but not both at the same time. So again, that's the guideline saying that the more complex your code is, the fewer collaborators it should have. And this pattern, this humble object pattern, it's nothing new actually. There are a lot of patterns in the wild that are the variation of this humble object pattern. And one of them is the MVC pattern, the model view controller pattern. Here we have basically the same thing. The model part in the MVC is the same as logic, the view part is the hard-to-test dependency, and the controller is the humble object itself. And what this pattern allows you to do is, it allows you to do exactly that. It allows you to separate model from the view such that you will be able to test the model part, the logic part, independently of that view, which is hard to test. And the controller is the humble object that coordinates the work between the two. So in the end, we have this picture where we unit test the domain model or algorithms, and we cover controllers with integration tests. And still, integration tests are important because it's also important. It's important to not only verify the logic of your application, but also how it integrates with external systems. And that brings us to the very well-known concept of the test pyramid. This concept tells you the ratio of different types of tests that need. So basically the content of your unit test suite in terms of the ratio between different types of those tests. So here the width of the pyramid represents the number of those tests, and the height represents how closely these tests emulate the end user. Here the unit tests part are there is the number of those tests is the largest in the test suite, but at the same time they don't represent the user behavior as closely as, let's say, end-to-end tests. End-to-end tests are the opposite of that. They represent they emulate the end user, but they shouldn't, the number shouldn't be as large as the number of unit tests. And we can also review this pyramid from the 4 components perspective. Unit tests provide you with fast feedback, and they are also very maintainable. That's because they are usually short and don't have any out-of-process dependencies. On the other hand, end-to-end tests provide you with the best protection against bugs because they verify a lot of code. And they are also have the best resilience to refactoring because, again, they are as distant from implementation details as possible. and the integration tests are somewhere in the middle. So that was the second part. That's where we talked about how to write effective tests. Now let's talk about mocks. Mocks are test doubles that allow you to verify the collaboration, the interactions between the system under test and its dependencies. And one of the benefits that the mocks provide you with is they allow you to split the object graph and only test, well, basically not create all these dependencies that the system under test depends upon, and just test the system in isolation from those dependencies. So let's talk about when you should apply mocks, when you should use mocks, and when you shouldn't do that. To do that, we need to talk about what kinds of dependencies there are in your project. All dependencies can be categorized into two categories: mutable dependencies and immutable dependencies. Mutable dependencies are the same as collaborators, and they themselves can be split into out-of-process dependencies and in-process dependencies. So out-of-process mutable dependencies are things like database, file system, external services, and so on. In-process mutable dependencies are basically domain classes like entities. So for example, again, if you test a user class and it depends upon a company domain class, and if that company class is mutable, then it would be an in-process mutable dependency. Immutable dependencies, likewise, they can be split into out-of-process and in-process dependencies. Out-of-process immutable dependencies are things like read-only API services, and in-process immutable dependencies are value objects or values. So the example with number 5, that I brought up earlier, that in that example, the number 5 would be an immutable in-process dependency, a value object. There are two schools that talk about mocking, classical and the London school. The London school tells you that all mutable dependencies, all collaborators, should be replaced by mocks. And the classical school tells you that all mutable out-of-process dependencies should be replaced by mocks. So there are two schools of thought, two schools of unit testing when it comes to mocking. Both of these schools are wrong in their treatment of mocks. And let's first discuss why the London school is wrong, and then we will talk about why the classical school is also wrong. Communications in your application can be categorized into two types. So the first type is external communications, and the second type is internal communications. So internal communications are things like when your domain classes communicate with each other, and external communications is when your applications talks to other applications. Here, internal communications are implementation details, and only external communications are not implementation details. And that's to see why we need to talk about how different applications evolve together. Well, when you develop your application, when you do, let's say, some refactorings in that application, you have to maintain the way your application talks to other applications. So let's say if your application puts some messages on a bus, then you will, even regardless of how many refactorings you do, you have to maintain the structure of those messages, because otherwise, if you deploy a new version of your application, then other applications will not be able to understand your application, the messages that you changed. So you need to keep the backward compatibility between your application and external applications. And that in turn is because you cannot deploy your application with those applications at the same time. So that could be because other applications are simply not controlled by you, or maybe it's the other application is developed by another team in your company, but still your deployment schedules are not the same. So when you have the situation where the deployment schedule is not aligned between your application and external applications, then you will have to maintain backward compatibility. And mocks are good for this exact reason. They are good because they allow you to solidify the communication pattern between your application and external systems. And so they are good for, let's say, verifying the communication between your application and the message bus. But they are not good for verifying the internal communications, because those communications are implementation details. They don't have anything to do with the end goal of your clients, of your customers. And you shouldn't use mocks for that, because that would be binding your tests to those implementation details. So again, this is our diagram. And as I said, in process, mutable dependencies should not be replaced by mocks. And that's why the London school is incorrect. Now let's talk about why the classical school is incorrect. Not all communications with not all external applications are part of the observable behavior, part of the contract. There are some types of external dependencies, communications with which are also implementation details. A good example here is the application database. That's the database that is only accessible by your application. So no other applications can read this database. Why the communications with this database is implementation detail? That's again because other applications cannot talk to that database directly, and because you can deploy your application simultaneously with that database. And because of that, your application and that database essentially becomes one system, because you deploy them together, and you can refactor the way you communicate with the database in any way you want. And as long as the observable behavior remains intact, other external applications wouldn't even care about that. So you can, let's say, for example, split the table into one, or you can even replace a SQL database with a NoSQL database. And again, as long as the external observable behavior remains unchanged, it will not affect your clients. So the communications with such dependencies are also implementation details. And that's where we need to split the shared mutable dependencies further into managed dependencies and unmanaged dependencies. Managed dependencies are dependencies, communications with which are not visible, are not observable externally. And that's something like application database, file system, and so on. And unmanaged dependencies are dependencies, communications with which are observable externally. Typical examples here are the message bus and SMTP service. And so only unmanaged dependencies should be replaced by mocks. That's because that's the only type of dependencies, communications with which should remain intact. And so they are part of the observable behavior of the application. Communications with managed dependencies are not part of the observable behavior, and so you shouldn't tie your tests to those communications. So again, mocks are useful, but they are useful only for communications with unmanaged dependencies. All right, that's basically it. Again, this is my book, Unit Testing Principles, Practices, and Patterns, and that's my website. So if you have any questions.
Thank you, Vladimir. If you guys still have questions, please don't forget about the area that we have for Q&A. But I guess we can start answering the ones that we already have. So I'll start with the first one. Regarding the safety net value of the unit test in your book and articles, you say that you should not mock the database or private external process as they are implementation details and will make the test brittle. Are these two things not against each other? Do we not get the safety net part by testing against this?
Well, again, you do get the safety net part, but as you saw in the beginning, you also have to balance it against the number of false positives you get. So if we go back to, let me find this. Yeah, so here it is. You will get these tests will find you bugs. So that's the signal part of the test, but they will do that with a lot of noise. So whenever you modify the communication with those external dependencies, those tests will break, and they will break not because you that's a bug, not because you introduced a bug, but because that's just the way your tests were implemented. They were tied to those implementation details. So when you evaluate your test, it's not only important to evaluate the signal part, but it's also important, critically important, to evaluate the noise part. And that's why I pay so much attention to the resilience to refactoring component. It's because you have to balance one against the other. Hope that it answers your question.
Thank you. I hope so. If not, I hope we get a reply. Meanwhile, let's see the second question from Nicoletta. When we have methods that are returning void and we call inside a method some dependency methods, what assertions should we make?
Well, it depends on what kind of dependency it calls. So if that dependency is an unmanaged dependency, which is usually what you verify in your integration tests, then you should replace that dependency with a mock, and then you should verify how exactly your system under test called that dependency. Otherwise, if it's not an unmanaged dependency, or if it's, let's say, some other domain class, then you should check not the interactions between the system under test and that dependency, but the state of that dependency afterwards. So let's say that, for example, in the book I brought up this example where you had, I think it was a company class and a customer class, and when you modify the email of the customer, it called the company class to increase or decrease the number of employees in that company. And so after you modify the email, here in this example, you will need to check the state of the company of that dependency afterwards. So the user and the company in this example, they should be verified together in a single unit test.
Okay. Next question from Nicoletta. Do you recommend do unit tests per a single class with mocking the dependencies, or to a combination of classes? If it is for a combination of classes, it is an integration test where you do not mock any dependencies?
Well, yeah, so in terms of taxonomy, the line is kind of blurred, and I wouldn't argue strongly against one or the other. You could call them integration tests, but I would still call them unit tests, because unit test is not something that verifies a single class. It's something that verifies a single unit of behavior. And that unit of, again, that's pretty subjective, but still it's a good guideline. And that unit of behavior, it can span it can span one class, one method, or several classes. It doesn't actually matter how many classes it spans. And I wouldn't call that an integration test, because that's still a one unit of behavior. So in the previous example with the user and the company, when you modify the email of the user, the affected the number of the affected classes is 2. So this modification affects both the user and the company. But still, this is a single unit of behavior, the change of the email, and you still need to verify both of the classes. And so to your question about, yeah, I recommend verifying single units of behavior regardless of how many classes they affect.
Okay, single units. Next questions. By controllers, you refer to the entry classes on a component like a web API controller from web API servers or a message consumer from a Windows service.
That's correct, yes. So that's basically the entry point where your application reacts to some external stimulus. So that could be the stimulus from the external user, like in web API controller, or it could be a message, yes, that you read and then react to with your application, yeah.
Okay. What should we do with a distributed application? There are multiple applications that access the database. It is okay to use a different database like H2 or SQLite in this case?
Yeah, I don't see any issues with using multiple databases. Well, that's more of an architectural question, not unit testing one, but still, if your use case, if your application requires more than one database, that's a perfectly valid use case. And in this case, if we bring it back to unit testing, you still need to verify how your application works with those databases directly. So you shouldn't mug them. And that would be the responsibility of your integration tests, where you set up your business logic classes, your database, and then check how the two cooperate.
Okay. Somehow related, another question is how to test raw SQL calls from the code.
You shouldn't. That's the whole point. The only exception here is that, well, if you write some library or something like an ORM, then yes, that SQL. Let's see. Yes, that would be the end result of this ORM library. But if you write just some enterprise application, then you shouldn't, because all these SQL calls are implementation details. What they allow you to achieve is they help you to do something with the database, to modify either the database's state or to select something from that database. And so what you need to do instead is you need to verify that end result. So either how the state of the database was modified or that the select query returned the correct data.
Okay. I think this question is related to an answer that you gave above. Can you please explain more what is it an unmanaged dependency? It is a component that we do not own implement. If a file system is a managed dependency, can we assert in a unit test that we saved something to the file system?
Correct, yes. So yeah, unmanaged dependency, I explained it better, I think, in the book, but basically unmanaged dependency is an out-of-process dependency which your application doesn't own. So for example, if you just develop an application, a standalone application, let's say it's a desktop application with some database, then you don't have any unmanaged dependencies because all the components are part of that application. The database itself and the UI and everything, it's just one big application. Well, maybe not big. And you don't have any unmanaged dependencies. But as soon as you start to integrate your application with external applications, then you will start having those unmanaged dependencies. So a typical example here is an SMTP server, and that SMTP server is still an unmanaged dependency because your communications with that SMTP server, which are emails that you send to people, those communications are visible to those people's applications, which is email clients. And so that would be an unmanaged dependency, and you cannot use it as is. Well, you can, but you shouldn't use it as is in your integration tests. You should mock it in your tests. And to your question, whether file system whether we can assert the state of the file system in the test, yes, we can do that. And that's basically what I recommend that you do. But again, it should be integration tests, not unit tests.
Okay. What about events? For example, a property fires an event to a different view model. How this case should be treated? I should mock the event or let it know?
So, yeah, I wouldn't recommend to test it at all because in this case, so I guess we are talking about something like MVVM, where you have a view model, and the view. So it's basically pretty similar to MVC. In this case, if you want to check how your application works as a whole, you should check. Well, I recommend that you leave the view part out of your tests and just verify how your view model works with the model and external components, because the view to check the view part, you basically need to do UI tests. And that would be the kind of tests that wouldn't couple to implementation details, because those events that you're talking about between the view model and the view, there are still implementation details between how your view model talks to that view. And I don't recommend that you test them, because that would couple your tests to implementation details. If you do want to check the UI, write UI tests. But if you don't, and in most projects, it's not necessary. And so if you don't, I recommend that you just instantiate the view model and check how it communicates with the database, with the domain model, but not with the view.
Okay. When would you consider the domain model entity private in process something that it is worth mocking? For example, when it is used in multiple layers. What about trying to achieve 100% isolation?
No, I don't think there is any use case where it would be justified, such mocking would be justified. So at least I haven't encountered one yet. So if it's private in process dependency, then you definitely shouldn't test it. And in this example where it's used by multiple layers, no, you just test those layers separately, and it doesn't matter if one of those layers, well, I assume it's not layers maybe, but multiple parts of the application, multiple components. So you just test those components separately, and it doesn't matter how many of those components use that dependency, that entity. And regarding the 100% isolation, it shouldn't be your goal. So the London school that I mentioned during the talk, it does advocate for 100% isolation, but it shouldn't be your goal, because again, you should target units of behavior with your tests. You shouldn't target the code itself. And when you try to isolate every pieces from each other and test them separately, what you do is you damage the cohesion between different parts of your application. So you're basically create tests that do not speak to the domain expert, and your tests, even unit tests, should ideally speak to the domain experts in their language. And when you try to achieve the 100% isolation, you basically don't do that. I mean, you violate this principle of speaking to domain experts. The only thing that the domain model should be isolated is not the only, but it should be isolated from the external services, such as the database, but it shouldn't be isolated from other domain classes. So if your domain classes talk to other domain classes, test them together.
Cool. We have a question about related to the first example about renderer. Should we also test all the renderers alone? If yes, then we have tested the behavior twice. Is this okay?
Yeah, that's a good question. Let's see how I would do that. Yeah, testing the same behavior twice is fine. Yeah, there's nothing wrong about that. And with integration testing, for example, you basically do exactly that. You first test with your unit tests. You test thoroughly your domain model with all the edge cases, and with integration tests, you test how all that works together as one piece. And that will necessarily mean that you will duplicate, well, you will test that behavior twice, first with unit tests and then with integration tests. As for this particular example, that is not exactly the integration test. So the test upon the renderer is not an integration test, it's still a unit test. So in this particular example, I think I wouldn't test those sub-renderers alone because they are quite simple and the resulting test would be trivial tests. And so I would just test the message renderer and that's it.
Okay. Someone is asking, wait, no unit tests for database calls at all? Only integration tests for DB collaborations?
Correct. Yes, that's correct. So the way you achieve that is you isolate your domain model from all out-of-process dependencies. And then in the book, I elaborated on that. But in short, yeah, you separate the two, not by replacing those database calls or database dependencies with interfaces, but just removing them altogether. Your domain model should only depend upon itself. It should be self-isolated. And so when you have this, so here let's say you have domain model, and here you have integration of controllers that integrate this domain model with the database. And so tests upon the domain model, as a result, they will not have to deal with all those external dependencies because that's the domain, the sphere of controllers, and that which itself is the sphere of integration testing. So integration tests cover controllers that do talk to the database, and unit tests cover the domain model that doesn't talk to any out-of-process dependencies.
Looks like most of the tests you're talking about becomes integration tests on one way or another. How it align with unit tests as the basis, tests of unit in isolation in Firemint?
Yeah, again, that's the definition. That's the kind of loaded question because it assumes that the definition of unit test is when you test just one class. I reject that that presupposition, and again, I wouldn't call a test that, well, it doesn't, unit test doesn't necessarily have to test just one class. It can test multiple classes as long as it focuses on one unit of behavior. And that's, again, that's a dispute between different schools of thought here. In London School, yes, you have this idea that a unit test should only test one class. In classical school, it's the way that I described it. So the classical school tells you that it's fine to unit test several classes together as long as they don't reach out to out-of-process dependencies and as long as they all focus on just one unit of behavior.
Okay, seems like we're going back to the unmanaged dependencies. The question is, we should use unmanaged dependencies only in controllers. In the domain logic, we can have only internal class dependencies that we do not need to mock in unit tests.
Yes, correct. So that's the idea of separation between the domain model and all external dependencies. And that will result you in not only good unit tests, but it will also give you a good architecture overall, because your domain model is complex enough already. You shouldn't put any additional complexity into it such complexity as, well, such responsibilities as communicating with out-of-process dependencies. And so you should strip the domain model of as many responsibilities as possible and keep it just to the bare minimum, to the domain modeling itself. And all the rest can be handled by the controllers, which don't have any complex functionality, but they do the orchestration between the domain model and the database and other out-of-process dependencies. That's the idea, yes, and that's the idea of not only good unit tests, but also the good architecture overall.
Okay, I think this was the last question that we had. Whatsoever, if there are any questions afterwards, I think we can maybe respond in the thread or something, if, yep. I don't know, something pops later. Thank you very much, Vladimir, for your availability and for being with us today. I saw that there are questions regarding to the presentation, if it will be recorded. It is recorded, and we will actually put details about the recording on the Meetup page of the community, so stay tuned. And also, if you guys have feedback for us or for Vladimir maybe, please also give us that feedback on the page, and we will take it into consideration for the next events.
Thanks everyone, thanks for having me. It was a pleasure to meet everyone. Thanks.
The pleasure, it's ours. Thank you.